Welcome everyone. My name is Mikhailo Golovnya. I'm a senior scientist at Salford Systems. And in the following presentation, I will be talking about MARS as an alternative to linear regression. Now, MARS itself stands for Multivariate Adaptive Regression Splines. It's the new data mining technology developed by Jerome Friedman at Stanford University back in the early 90s. And chronologically, MARS is positioned between Jerry's original work with Bryman, Olshan, and Stone on CORT back in early 80s, and Jerry's most recent work on stochastic gradient boosting in terms of TreeNet, as well as some of the more recent and interesting post-processing techniques for TreeNet models, as well as Leo Bryman's random forest models. So MARS stands for Multivariate Adaptive Regression Splines, and it could be interpreted as a modification of the original CORT engine to better handle regression side of things, where instead of building a piecewise constant models, we would now build continuous piecewise linear models, and hence the utility of first-order linear splines, etc., etc. I will start by reminding you the essence of the modeler's problem. The modeler's job is to find a way to accurately predict y given some variable x. Y is usually a univariate case, whereas x's are some kind of vector of measurements. Usually you would have a mixture of continuous and categorical variables of all kinds of different sources. The modeler's problem in the regression context can be thought of as an approximating the generic function y as some function f of x plus noise, and the noise itself absorbs all kinds of randomness that surrounds conditional distribution of y given x. The problem here is that the modeler usually doesn't know enough to do this as well as we would like. In other words, what usually happens is that the modeler doesn't know which variables to use. I mean, we might know some of them, but not necessarily all of them, or usually we know more variables than are actually needed in order to build a successful model. And the second, which is a lot more crucial characteristic, is that we usually don't know how variables combine to generate y or f of x in the first place. F of x is oftentimes called the response surface, and it all boils down to trying to either guess or in some systematic way construct the true ultimate shape of the function f of x, which in most regression cases communicates the nature of the response surface that we are looking for. Now, even if we did know the answers to the first question, it would have still be quite difficult to guess based upon our a priori tools and means and understanding on what the actual shape of the function f should be. Hence, that proliferation of the conventional regression techniques and approaches, which are all essentially based on the trial and error, kind of guess the shape, try to fit it to the data that you have, see if things are looking okay. If they're not looking okay, guess another shape. Then you keep doing it over and over again until, in most cases, you simply run out of time and can't do anything with it anyways. I will illustrate the inner workings of MARS as well as some of the conventional approaches using a Boston housing dataset. It's a publicly available dataset. It dates all the way back to 1970, and it records demographic as well as housing information in 506 census tracts in the city of Boston in 1970. And the goal is, in the original study, was to find a possible relationship between quality of life variables and property values. The property values were recorded as median value for each census tract, And the demographic variables are presented over here. So these will constitute the list of potential predictors. So in a nutshell, what we want to do here, we want to build a regression model that explains MV as the target variable based upon some of the variables that are presented here. Things like house size, crime rate, pollution rate, age of neighborhood, proximity to downtown, etc., etc. A typical modeling situation, we don't know exactly which variables are most influential. There's also a great degree of mutual dependency among these predictors, as is naturally expected. We have all kinds of difficulties as far as nonlinear relationships. It's not likely that each of these variables will contribute in a plain old linear fashion. And this can be further illustrated by looking at a so-called scatter matrix, or the matrix that shows both individual variable distributions for a selected subset, including the target variable, as well as the mutual scatter plots between the target variable and the selected subset of core variables that, as we will find out soon enough, happen to be one of the most influential in the model building process. Now, by looking at these scatter plots, even though the exercise itself is not quite rewarding, and there are tons of counterexamples that can be constructed that illustrate how misleading some of these scatter plots could actually be. But all of those issues aside, even if you look at these scatter plots as they are, it becomes clear that this particular situation would pose some kind of challenge to a modeler. It is not likely to have pure linear relationships. There's a great degree of mutual dependency and all kinds of seen and unforeseen anomalies that one might typically find with the regression data set. That's one of the reasons why the original problem was presented as a challenge to the data miners and statisticians back in the 70s. And the guys who actually won that challenge spent about 2 months of a real productive, full of man-hours work in order to self-construct by the use of trial and error the model that Mars will be able to reproduce roughly within minutes. And that's the whole point of introducing Mars. Let's take something that has been known to be quite a challenging data set, and it's also devoid of any severe technical load, so it's likely that anyone who sees Boston housing data set understands the nature of the modeling problem. So we picked this data set to illustrate all of the key characteristics of Mars, its key advantages and benefits. Again, to repeat myself, in the global parametric modeling, which is typically represented by modeling tools like linear and logistic regression, the global parametric modeling will be characterized by rapid computations, but it's only accurate if the specified model is a reasonable approximation to true function. In other words, nothing in the algorithm itself will help you as the modeler to build the actual function f of x. It is assumed that you are taking matters in charge, that you define and control what the shape should be, and you're delegating the modeling, the estimation technique, only the small task of finding out the best fitted coefficients for the model that you have initially guessed. So it is, in the essence, a process of trial and error. Sometimes you're looking at the underlying subject matter, underlying theory, and it is quite possible to actually know exact shape of the relationship, but unless you're dealing with a simple physical phenomenon like Boyle's law or Ohm's law, for the most part, it is unlikely. And then it becomes process of trial and error. You're fitting one shape, you're seeing whether it looks right. If it doesn't, you're trying to essentially use your intuition, your common sense, prior experience, and this is where a great deal of craftsmanship actually kicks in. And that's all characteristics of global parametric modeling, something that we want to deviate from when we move onto the modern scale. A typical example of a global parametric modeling is a so-called multiple linear regression. Well, in this case, it's illustrated by a simple linear regression where I took one variable, LSTAT, which relates to the poverty rate in the neighborhood, and attempted to fit a straight line solution with respect to the house values. As you can see, this model, its biggest advantage is that it's extremely easy to fit. It gives us a very robust and simple description of the underlying model, but it is likely to have missed interesting pieces of the behaviors of our predictions and the tails and in the center. If you look at this curve or the straight line, then you can see that the actual predictions are somewhat exaggerating true conditional means in the center and underestimating true conditional means in the both tails. Of course, one might say you could take a look at this plot and immediately guess that it has to be actually some kind of inverse function or something of the alike functions. But things are not that easy to say when you move onto the multiple dimensional scale, and when you simply, our brain has no power and capability to look at the similar plots in multivariate spaces. And that's one biggest problem that we have to challenge, to face, and the problem that essentially triggers all of that extra development and search for fully automated techniques that would be able to extract and learn about the underlying response surface from the data set itself. So that in particular brings us to the new realm of non-parametric modeling. And we want to learn more about the best model using the data set itself. Now that covers all bunch of typical practical situations. Sometimes the underlying model is not defined. I mean, it's not stable. It could vary from day to day, month to month. Sometimes, in many cases, underlying scientific theory is not available. Sometimes you deal with models that drift in time and drift in space. So it is highly unlikely that you will be able to guess the exact nature of that pattern and development as it progresses. I mean, the sad truth of the matter is that all typical life phenomena are difficult phenomena to study. And unless you have a bunch of simplifying assumptions, in all typical situations, it is plain unlikely that everything will be governed by simple linear or quadratic solutions. So we want something that learns from the data itself. We want something that gives us better means and ways to understand the underlying nature of the process, its evolution, its development. All of these approaches are going to be very compute intensive. And the fully non-parametric modeling develops models locally rather than globally. This is to reflect the initial kind of straightforward fact that we are technically looking for a conditional distribution of y given x. Therefore, in the presence of infinite amount of data, we could focus at the given x and simply observe the behavior of y at the given point. Now, that essentially renders that idea of localizing a model building process down to only important subset of the data as a kind of fruitful, because it in some ways approximates what is happening at the conceptual level. And the way it's usually done, somehow we identify a small region of data, for example, low values of x or middle values of x, and there are a lot of technical issues that arise as we are trying to do that. So I'll skip all of that part. And then you summarize how the target variable behaves in the local region. Well, the general idea here is that the weather in Los Angeles is not likely to be connected by the weather conditions in the New York. And the more local you go, but not too local. But in any case, if you're looking at a somewhat confined area immediately surrounding the current point of interest, it is most influential and contributing in the actual predictions at that region. And then you develop a separate summary in each region of the predictor space. Of course, in many cases, there are some situations where analysts require some cross-region smoothness, and that's in some cases an important topic to cope with. It's also very important not to be overly data-driven. Whenever you enter into non-parametric modeling, what usually happens is that new concern of the phenomenon of overfitting. The problem is that when you deal with the data set available to you, it already has every pieces of information frozen in it, including some concrete implementation of the noise pattern. And if you're learning overly aggressively from that frozen data set, it is likely that your learning will include at some stage and point that extra noisy component. And you may want to avoid it, and it's important to have certain mechanisms within the algorithm itself that will help you in that kind of direction. Now here is a typical example. As you will see, what is shown here is a Mars solution for the univariate case using LSTAT and MV. Suppose that we knew somehow that our linear function changes its slope at the values around 4, 5, and 22. Now this way we could have built localized linear models at each of the subsets of LSTAT, and in addition to that we could also introduce the requirement that our models have to join and merge smoothly at the points of transition. So if we comply with these intuitive requirements, the end solution will be given by this black line, and as you can see, it combines the useful features of classical regression model. In other words, each segment here can be explained and described as a simple analytical form. On the other hand, we all of a sudden have the advantages of the non-parametric solution because the fit of the rightmost segment is almost under no influence by what happens on the leftmost side of this curve. And that's a very useful kind of appeal of this approach. We are kind of attempting to build a piecewise linear regression solution that takes into account some of the local features of the data set at hand. And in that regard, it behaves as a pure non-parametric solution, but it also preserves some of the nice analytic characteristics of the conventional plane regression model. Looking ahead, the only difficulty that arises here is the location of the actual transition points. Now, in some of the earlier attempts, people would simply impose those transition points beforehand, and it's quite feasible when you have univariate or maybe bivariate kind of situations. But in the multivariate sense, for the same problems that we have already mentioned before, it is unlikely that you will be able to guess beforehand the actual locations of those transition points, or any attempt to impose a systematic grid is ruined by the phenomenon generally known in science as the curse of dimensionality. The larger the number of dimensions, you have the exponential explosion of possible number of combinations for any predetermined grid that you might impose on the data set in a multivariate sense. It turns out that Mars, at the core of the Mars machinery, is the solution to this nasty problem of identifying different regions. And once the regions have been identified by Mars, the end solution is given in pretty much the exact same form as you're seeing on this slide. So in a nutshell, what Mars is doing, Mars is an automated way to build a piecewise multiple linear regression problem such that the transition points, we call those knots, are found automatically without any contribution from the modeler himself. And that's a very appealing part. That's what stands apart from the classical conventional nonlinear regressions where you as the modeler would have to impose certain nonlinearity, and then simply use the nonlinear regression approach to estimate some of the coefficients using Newton-Raphson approach or all kinds of other optimization theory results. In the case of Mars, you are going the way beyond that conventional approach. You are actually asking Mars as the algorithm to search for the optimal transition points and present the solution that has both the results of that search and the results of fitting the piecewise linear solution in that space. Key-spline, therefore, is not. Not is what marks the end of one region of data and the beginning of another. It basically controls where the behavior of the function changes. Now the model technically becomes global between knots. I mean, you could use as simple as a linear regression solution between two knots. But because of the knots that essentially constrain your model to a local region, the overall solution is no longer global. It gets in a truly localized fashion. Now, in a classical spline, knot positions are predetermined and are often evenly spaced. We also know that this is unacceptable in terms of the curse of dimensionality and all of the related issues. So in Mars, knots will be determined by some kind of search procedure. And 90 to 95% of the total running time of Mars will be spent on that search procedure. Only as many knots are needed to end up in the Mars model, and the typical Mars solutions vary from tens to a couple hundreds. If a straight line is a good fit, Mars might as well figure that out. So technically, a multiple linear regression could be considered as a primitive subset of the whole family of all possible Mars models. But it's likely that in all practical situations, Mars will find presence of certain knots that locally improve model performance by at least a certain amount. The following example sort of illustrates all of the key characteristics of the Mars process. I have the true conditional mean of y given x in the univariate sense on the left panel. And I also have a true data set generated for that model structure on the right panel. So there's a little bit of noise added. And now we want to build an automated way to search for the optimal placement and location of the knots. Now, it turns out, computationally, it's not feasible to search for multiple knots simultaneously. We have to do it one knot at a time. For example, if I want to place only one boundary in this plot, then I could technically try every observed data point as a potential knot location, as a potential knot placement. Now, once I pick it as a potential point, the transition point, I could fit one straight line solution to the data on the right-hand side and another straight line solution to the data on the left-hand side, and at the same time require that both solutions merge at the transition point itself. Now, conceivably, I could try this experiment at every available data observation. And if you have n observed values, technically you need to try up to n-1 different positions for the knots. That's a feasible operation. It's linear in the data set size, and for each potential knot placement, you could check the performance of the resulting fit of two segment solution, and you could search for the most optimal knot location, which is not that difficult to see in this case. Well, happens to be somewhere around the central flat piece of this curve. Once the first knot is being found, the process repeats itself. It searches for the next best knot while keeping the first knot fixed. The reason why we cannot look at many knot placements simultaneously is because trying to search for k knots simultaneously would bring the complexity of the algorithm to the order of n to power k. And that complexity with the K2 and above is something that would kill performance of our algorithm on the data set of any decent size. So in the traditional implementation of Mars, because of all of these complexity issues, the strategy is to build a model one node at a time, sequentially, with the subsequent backwards cleaning step. The full details of this process are described in our Mars training class. This class is just a brief introduction for those who want to get the flavor of Mars without getting into all the technical gory details. But in any case, introducing one node at a time illustrates in a rather nice form how Mars progressively discovers the true nature of the shape in this particular data set. Also notice that the knot that is being introduced in the first place is actually a fake knot. It's not really needed in order to communicate the true shape. It's, in a sense, it's an artifact of that sequential forced one knot at a time approach to the whole process. So once we get at the end of the 6 iterations where 6 knots were introduced, Mars will switch to a backwards elimination step where it kind of re-examines all of the available knots, again, one at a time, removes least contributing knots, and at the end of that process we get a sequence of models of varying complexity that could be evaluated based on the test sample in order to suggest optimal model, as well as we will discover that the remaining 2 knots at 30 and 60 are likely to be the most contributional, and they will be preserved until almost the very end of this backwards elimination process. As far as the implementation of Mars algorithm itself, we need to talk about basis functions. Now, what are basis functions? The basis functions is the machinery behind knots. Things that were initially introduced geometrically in the previous construct can be re-expressed in pure analytical form as the concept of basis functions. And that's basically the first point worth mentioning here. As far as the basis function itself, as the analytical machinery designed to present knots, they can be introduced in 2 different flavors. On one side, you can consider transforming variable x according to max of 0 and x minus c, c being some kind of threshold within the full span of x, or in its mirror form, which is max of 0 and c minus x. It turns out that parameter c is what controls where the future knot will emerge. And technically, any of these basis functions could be interpreted as a 1/2 of the equivalent of a single geometric knot. And again, all the details are represented in our training class. Here I only show some flavor of the mathematical objects that Mars is dealing with. So to make long story short, each basis function is nothing but a primitive transformation of the original variable x that reduces the useful range of that variable to a subset of values, zeroing out everything that's outside of that subset. One useful characteristic of the basis functions is that when you take transformations like shown here and start multiplying them, and when these transformations are based on different variables, you all of a sudden reach a very useful concept of region-specific interaction. And that's one point in favor of using Mars to handle some of the problems where such interactions might actually arise. The next slide shows a number of basis functions constructed with different values of the parameter c. And as you can see, c indeed controls the location of the knot. And the fact that the basis function is technically 1/2 of the knot is reinforced by the zero values of the transformation to the left from the C parameter. Another useful way to look at the basis functions is in terms of transformations and their structure as far as mutual dependency. It turns out that as long as you have two basis functions based upon the same founding variable with C values reasonably apart, the presence of zeros in the overlapping part of those basis functions guarantees that the two basis functions will be linearly independent. And the same goes for any number of basis functions. So, in other words, from the analytical point of view, it does make good sense to construct Mars model as a multiple linear regression solution that uses multiple basis functions based on the same variable. And there will be very little danger of running into difficulties like multicollinearity or all kinds of artifacts related to the mutual dependency of input vectors. Armed with that kind of general knowledge, let's see how one could use basis functions to essentially emulate a spline solution. Here is a one-term model that explains MV in terms of indus. That indus minus 4 was the plus subscript, is a shorthand notation for the basis function. And what it says is that MV, when indus is below 4, is going to be this constant. However, when indus exceeds 4, that constant is being progressively diminished by a linear term with negative slope. If you look at the graphical display of that same approach, then you see that indeed when indus is below 4, MV is a constant, then we have a gradual decrease. The next slide, we build a model up by adding another basis function based on the same variable indus, but this time with a not value at 8. So this time, when indus is below 4, both basis functions are turned off. When indus is below 4 and 8, only first basis function contributes with a negative slope of 2.4. And when indus is above 8, the second basis function contributes on top of the first basis function as an adjustment slope. So jointly, what we have is the initial horizontal flat segment for indus below 4. Then we have the negative slope segment between 4 and 8 with a slope of negative 2.439. Then when indus is above 8, that negative slope is positively adjusted by the extra term of 2.215. The joint sum of these two slopes remains a negative number, and therefore the overall contribution remains negative, even though on a somewhat more gradual scale. Notice that basis functions of this form and shape with the variable on the left and the cut point on the right will not be able to generate a negative, or some kind of slope on the very left-hand side of the equation here. In other words, sticking with only direct flavor of basis functions, we can't avoid having a constant flat segment on the very left-hand side. This necessitates the introduction of that second flavor of basis function, which I already mentioned as mirror images. And in this case, we could introduce a third basis function, BF3, where the value of the naught at 4 and the indus itself have been flipped. Now that basis function operates to the left from the naught, and it's zeroed out above value of 4. So the joint contribution of these three basis functions, and notice that we could construct basis functions according to their definitions and then simply fit a multiple linear regression using these three newly constructed variables as individual predictors. So the result of that multiple linear regression is shown here. So you get to see the intercept and the three slopes But the difference is that this time, this third basis function, which is set as 4 minus indus, operates to the left of this 4 value. And because in its structure it has indus with a negative slope, the positive coefficient of 0.925 effectively becomes a negative coefficient that explains the analytical structure to the left from the value of 4. All of the remaining basis functions are turned off in that region. Once indus crosses the value of 4 and goes above it, the mirror basis function turns off. The remaining basis functions start kicking in progressively in a pretty much same fashion as we have already seen before. The end result of this process is the joint shape that looks like this. Now, as far as the Mars goes, it now becomes clear that this search for possible knot placement is nothing but the search for basis functions. Now, each variable spawns a fixed number of different basis functions. Now, you can also add to this the possibility to multiply basis functions in a pairwise, triplewise, etc. manner. And that gives you the working set of all possible exhaustive searches. It is done one basis function and one variable at a time, and it's done in a sequential way to build the model and then subsequently to reduce model by backwards elimination. The end result of the Mars run technically is the model that is described in basis functions, and the slopes and the coefficients can be interpreted along the same set of lines that I've just currently spoke about. In our Mars training, we have a more detailed set of examples, and we revisit this concept of interpreting individual coefficients. But basically, the real power of Mars is in its ability to identify the proper locations for all of these knots, as well as fit the AND model within that found configuration. So the Mars algorithm, in the most general sense, could be summarized as follows. Start with a simple intercept-only model, which is essentially the initial guess model that fits constant everywhere. Then you search for all variable knot combinations as presented by the available finite set of all possible basis functions. And you are searching for the combination that improves model the most or worsens model the least. In this case, technically, if you were to do things by the book, you would have to run all these individual regressions and it would still have resulted to a very lengthy process. The genius of Jerry Friedman is that he found out very effective ways to reduce the complexity of that search, to eliminate the need or avoid the need of recalculating variance covariance matrix over and over again, and essentially use and employ all kinds of smart shortcut techniques to facilitate this direct search for the next available basis function. So, I mean, the part of the machinery is quite sophisticated. I would say Mars is one of the most complicated and complex techniques available to us at the actual internal code and theoretical level. But fortunately, none of those difficulties are even needed to be aware of in order to become an effective Mars user. So as long as you understand the nature of the phenomenon, the way the process goes, you will be okay in using it. And the process is naturally repeated until the given pre-specified number of basis functions have been added. Then Mars switches to backwards elimination, where basis functions are being progressively eliminated one at a time. And then it does the optimal model selection. And the original versions of Mars optimal model selection was inspired by conventional optimal model selection approaches like generalized cross-validation or penalized mean squared errors, things like that. In the most recent implementations of Mars, we are switching to the explicit learn-test partition on the dataset, in which case the entire Mars process evolves on the learned dataset only, but the resulting sequence of models obtained as the result of backwards basis functions elimination, the so-called cleanup state. That sequence of models is being evaluated on an independent test sample or by using a genuine cross-validation in order to suggest optimal model performance in terms of mean squared error or mean absolute error. This is the way a typical Mars model might look like. This is an extract from a Boston housing dataset, which we are about to run. It has two pieces, the transformation section where individual variables are transformed into basis functions equivalents, and also note some of these cross-product terms. And the basis functions themselves serve as legitimate terms in the multiple linear regression equation. And you never, don't be scared away by the length of these multiple linear regression, because we have already commented on all of these variables not being linearly dependent. So it's likely that even when you have such an enormous number of terms, like 20, 30, 50, in the final model equation, when you look at the significance values and the p-values, those are likely to be very small, to the point that they are not really useful for ultimate model diagnostics. There's too many things that are happening as far as the search goes to render all of the conventional regression approaches and interpretation are of dubious value. Mars gives you variable importance, which are basically variables' ranks according to their contributions to the end model. And Mars also gives you so-called contribution plots, where all basis functions based on the given variable are gathered together and presented as one kind of continuous shape. It's pretty much to relieve you of the task of interpreting coefficients and signs and whether the basis function is direct or mirror in any given specific case. It's also a nice interpretational tool in terms of how the model is actually trying to explain the dependency of the target variable with the given set of predictors. Mars also goes beyond 2D plots, and it is capable of showing joint contribution of two variables as long as they are occurring in an interacting pattern. And that's pretty much a very useful extra added insight. Illustrates how some of these different pieces are jointly combined in order to produce a potentially complicated individual response surface. As the summary, and we will see it in a moment, if I take Boston housing dataset and run it in a plain old multiple linear regression, I can hardly go above 73% as far as the R squared goes. Whereas running Mars increases R squared all the way up to lower 90s. You can also check the performance in terms of mean squared error. As far as the running time, Mars model is amazingly only 3 times as slow as the multiple linear regression problem. On the larger data sets, you will probably observe longer running times, but they are still quite accessible and decent. And it's mostly due to all of these shortcuts that Jerry Friedman incorporated inside of Mars that make the entire process feasible, even on very large data sets with large numbers of variables and large numbers of observations. Now, notwithstanding all of these comments, it might still be beneficial to reduce the list of input variables before you actually run Mars by employing things like cart runs, treenet runs, random forest runs, etc. because even though Mars is capable of running all of these individual variables at ease, it is still a very computationally intensive technique. There's a lot of internal adjustments and matrix manipulation and all of that that goes on. And things can be helped and improved dramatically when you feed a somewhat smaller set of variables. So if you have any means and tools at your disposal to reduce the input subset to a more representative sample subset, by all means, go ahead and use it. Same goes for missing values, for high-level categorical variables, and everything. Even though Mars itself in its core implementation is capable of giving you effective support for categorical variables and missing values. The details of all of that are also explained in our regular Mars training class. So the conclusion here, as far as the formal definition of Mars, is that Mars uses first-order splines to automatically find the solution to multiple nonlinear regression. It conducts both automatic variable selection and produces variable importance and variable contribution plots. So you not only see which variables are important contributors, Mars actually tells you exactly how those variables are contributing to the overall modeling shape. And because of the Mars enormous flexibility and automation, one may quickly unravel complicated internal data structures and explore the nature of the relationships in your data set in the subject of study. So that concludes that theoretical exposition of Mars. Well, it turns out that in order to understand Mars models, you need to get a little bit of basic training in terms of basis functions and reading some of these equations. Once you're past that initial stage, you will have no difficulties whatsoever reading the actual Mars models and being able to freely interpret the results and even improve the results. So I will illustrate in the second part of this presentation the general ideas behind Mars on plain run based on Boston housing dataset. So what you're seeing in front of you is the Mars GUI interface. We currently have it available only for Windows platforms, even though Mars itself as the command line application is available on virtually any alternative platform out there. It includes all flavors of Unix, Linux, Mac, and beyond. So if you do have an exotic alternative operating system, talk to us. It's likely that we will have a command line implementation available for you. But for the majority of the beginners, I would recommend using the GUI version of Mars on Windows because it helps you understand how all the different pieces are being put together. Plus it has all that graphical capability to display Mars results, which otherwise would be more difficult to deduce based upon the model equation itself. It's analytics engine, so it assumes that the dataset is already prepackaged formed, ready to use. So in my case, I'll start by opening a Boston housing dataset. And all I need to choose is my target variable, the list of potential predictors. Now notice that Mars does support binary targets and does it in a somewhat artificial way. When the target is 0 and 1, it builds internally a nonlinear kind of regression model that treats the target variable as a continuous target that just happen to have values of 0 and 1. But once the model has been built, at the post-processing stage, the internal Mars machinery converts the continuous prediction into a fixed kind of classification, whether it's 0 or 1. In addition to that, you yourself could also take the resulting Mars model definition and refit it in the conventional logistic regression using stepwise approach. That would correct for all kinds of linear anomalies at the tails as well as recover true shape in the log odds space. So do keep that in mind. Some of our clients have been quite productive along those lines. But in my case, the target is pure continuous, so it's a plain old nonlinear regression setting. The Mars itself, let me quickly illustrate what happens if I disable Mars component by declaring all variables as non-transforming and effectively fitting a plain multiple linear regression in this case. So if you take Boston housing data set and fit a multiple linear regression, you will end up with the model that essentially approximates everything as straight lines, and you have all of the common interpretations in terms of slopes and how much the target changes when the input predictor increases or decreases by 1 unit. The model itself gives us about 74% R squared on the learn data set. Now, if on the other hand, I go ahead and allow Mars transformations. Now, in order to fully exploit Mars characteristics, I need to allow larger number of individual terms. Something that could not be done in a multiple linear regression because it would basically accommodate at the most all of the variables that I fed, but no more terms than that. In the case of Mars, I will ask it to build, say, a model with up to 40 basis functions, and the rest of the settings will remain unchanged with disabled interactions. So max interactions is set to 1, which is technically to disallow all interactions. So if I now go ahead and build my best model, the R squared immediately went up to 88%. If I look at the curves and surfaces, it does show up nonlinear dependency in some of the key variables in my model. And notice when you look at the RM compared to some of the previous plots where linear regression was approximated by a straight line, in this case, Mars really uncovers some interesting local regions where the behavior drastically changes and regions where the behavior pretty much remains unchanged. And you could study all of the remaining plots, including distance to downtown, that shows some real strong dependency in a small distances followed by a gradual decrease for much larger distances. And ultimately, I could also ask Mars to build a model with interactions, and this time I can improve predictive accuracy as far as R squared goes all the way up to 93-94%. The basis functions now will include some of the cross product terms, and when you look at the curves and surfaces, some of these are now reported as having joint interactive patterns, as you can see from some of these displays over here. Well, I will leave it at that. If you are interested in learning more details about Mars implementation, you're welcome to attend our online and in-person Mars training, where we cover everything in greater length with all of the theoretical exposition in detail. But other than that, you should be able to start running Mars on your own without much trouble. And if you're interested, go ahead and get free evaluations. Download Mars off of our website. Play around with it. Chances are you will find a lot of interesting and useful discoveries on your data set. And hopefully you'll come back and we'll be able to talk at a greater length. Thanks for your attention, and I wish you all the best.